Hello and welcome to Spacetime. I'm joined in the studio by Mr. David Moore of Astronomy Ireland, and today we are going to be taking a look at Mars. Mars, obviously a planet that has captured the imagination throughout history. So what is it exactly that gives Mars that deep red colour?
It's basically iron compounds. Really, it's like rust.
Okay.
There's a lot of iron oxidized in the soil. And we see red sand on the Earth. It's the same thing. There's lots of iron mixed in with rocks throughout the solar system, the Earth included. We're all made of the same stuff after all. Nothing exotic on Mars compared to the Earth. And so it's that sandy dust that we're seeing. Okay. And the problem is the water escaped a long time ago, probably because Mars' core set solid. Ours is still molten, as we see from volcanoes and earthquakes all the time. But on Mars, it's almost certainly set solid, or it's certainly not as fluid as the Earth is. It's no magnetic field that doesn't protect it from the radiation of the sun, and that stripped the water away and the atmosphere over billions of years.
So there's evidence that Mars used to be a rather vibrant planet, not dissimilar to ours.
In the first billion years of Mars history, it was probably similar to the way the Earth is now. That it was a lot of water on the surface. The atmosphere was thicker. Even though it's a smaller planet, it's half the size of the Earth. Gravity is about a third. So you'd only weigh a third of what you weigh here on the Earth. But there wouldn't have been oxygen and things like that because plant life on the Earth seeded our atmosphere with the oxygen that we as animals need to breathe in. But that could have happened had life had a chance to evolve. And the big question is, did life evolve? Because it seemed to evolve on the Earth very quickly after the Earth cooled down and then got killed off by the conditions getting terrible. Or did the life somehow go below the surface and it's been eking out a miserable existence since then? Maybe it went extinct at some stage between the two. And there are missions trundling around the surface of Mars now, trying to characterize the environment, and other missions plan to go there to look for the actual life. And of course the missions will go to Europa as well. So hopefully during our lifetime we'll find out, is there life in the solar system? And if there is, if life exists in two places in the one solar system, and we think there's about 40 billion Earth-like planets in our galaxy alone, then the universe could be teeming, at least with simple life, and who knows about intelligent life. I mean, it could actually be a Star Trek scenario out there with lots of alien civilizations. The only problem is the distances in space are enormous. And it's really hard to imagine how big they are. And not only with technology, but the kind of physics that we understand and the laws of the universe. It's very hard to understand how you could generate a system that would enable you to move between the stars. Moving between the planets takes decades with current technology. The stars is going to take hundreds of thousands of years. And on human life scale times, that sort of makes it difficult to see how we're ever going to travel that way. But you know, there are theoretical ideas like wormholes and the like, which are highly hypothetical. But if they turned out to be real and we can tap them, maybe we'll find that technology in the future.
Exactly, it'd be the shortcut to the stars that we need. And in terms of travel, I mean, obviously we've landed on the moon many years ago, and there was the political impetus to get there. Is there still the same drive to get to Mars? Like, are we ever going to get there soon?
There is a little bit of a race going on. The Chinese built their own space station now. They've got their own rockets that can put people into space. The Russians, of course, can put people in space, and the Americans and the European Space Agency, working with the Americans, can do it as well. So only the big nations can currently do it. And if the Chinese were to get involved with the Americans in a race to Mars, then that could bring back sort of some of the Cold War scenario that we had, that it would become a question of national pride. But it's probably more likely that because it's so expensive and so difficult, that it'll be an international mission and people will go to Mars. You know, as we overpopulate this planet, we're going to need somewhere else to live. Mars is the most hospitable planet, still not a nice place to live. But with relatively simple technology, you could live on Mars. And that's more or less what we did when we conquered the Americas. The first pilgrims there died in their masses because they didn't know how to farm the land there. It was actually the locals, the Native Americans, that taught them how to farm there. We wouldn't have the USA as the power that it is today if it weren't for that. Now, there are no Native Americans or Native Martians on Mars to help there, but hopefully our technology will enable us to actually overcome any problems that you find when you actually try to live on Mars.
One of the most forbidding and mysterious objects in the universe is a black hole. Massive and powerful almost beyond belief, black holes warp space and time itself. Just what happens inside the centre of this churning heart of darkness is still a mystery. I asked David to tell us more.
Well, the strict definition of a black hole is just an object that has such strong gravity that nothing can escape the surface, including light. So technically, if light fell on it, it would go in, nothing can ever shine off it, it would be black. Turns out actually they're actually the brightest objects in the universe, because as things go screaming down this cosmic plug hole, never to emerge again, the friction that they cause actually makes them glow extremely hot, hotter than white hot, into the ultraviolet and X-rays. And so black holes end up causing the brightest things in the universe. A quiet black hole, minding its own business, will be black. So they're absolutely fascinating objects. And to crush matter down to make the gravitational fields that you need is phenomenal. You take the Earth, for instance, and you would have to shrink it down to something the size of a marble.
Wow.
And there's no technology that can do that. But it turns out giant stars, when they end their lives, and these are stars much bigger than the sun, they get very unstable in their cores, and they end up exploding. And that can crush the core of the star to create a black hole.
Black holes are fascinating objects that have many intriguing features. What you are seeing is an artistic representation of a black hole. The rotating ring of gas in the foreground is called the accretion disk. This is caused by the gravitational energy of the black hole as it churns in space. The immense friction and gravitational energy are converted into heat and then light. We also see a ring of energy above and below the black hole in the centre. This is not a separate entity, but the same accretion disk just mentioned. The intense gravity around the black hole bends the light up and over and also underneath the black hole. This is known as gravitational lensing. This same effect distorts the light of the stars behind the black hole as well. The event horizon in the centre is the point of no return. Once something passes this crucial point, it can never ever come back out. At this point, nothing, not even light, can escape the power of the black hole. What happens past this point is unknown.
It turns out now we're pretty sure that all galaxies have a black hole at the centre. Some of them have giant black holes. The one at the centre of our galaxy is about 5 million times the mass of the Sun, so 5 million suns stuck together, if you like. Wow. But there are ones that are 1,000 times bigger than that in other galaxies. And the question is, why do some of them have black holes that are 1,000 times bigger? Another interesting about the black hole is it turns out it's controlling the development of the galaxy itself. And it was an Irishman, Dr. John Magorian, who figured this out. It's called the Magorian effect, after him. And if the black hole didn't slow up the evolution of a galaxy, then the Sun wouldn't have been here in a more or less stable galaxy long enough. And so we wouldn't have had time to evolve. So we owe our existence to the black hole at the centre of our galaxy. And probably all other galaxies, if they have intelligent life, have a similar story to tell.
They have the same depth.
It's remarkable, it's a nice Irish angle to the whole thing.
Exactly, yeah. So obviously we see black holes when objects stray too close and get sucked in towards the centre, but it's not just space they distort, but time as well.
Yeah, crazy things happen at the surface of black holes because Einstein became famous for his theories of relativity, and the main thing he assumed was that the speed of light is the maximum speed in the universe. No thing can go faster than that. And once he made those assumptions, did the mathematics behind it, he came up with these great theories of relativity that made him so famous. And with a black hole, when the matter falls in, you get what's called time dilation. And this would happen even if you didn't have a black hole, but you travel very close to the speed of light.
I see.
It's a relatively simple piece of mathematics. They teach it in first year university. Nothing overly complicated about it. And it shows that time will, if you could hit the speed of light, if you and I are traveling speed, time would actually stop. So somebody, if they could look at us whizzing by at the speed of light, and they saw a clock in our spacecraft, the clock would stop. Well, if we were looking out, we'd see their clock speeding up. You get all these crazy effects.
Space and time are so closely linked that the term spacetime was coined to describe it. When a black hole distorts space, it also distorts time as well. This simple graphic will help visualize it. Spaceship 1 and 2 set off on their journey at the same time, and so their clocks are in sync. However, Spaceship 1 is not going to take the same route as Spaceship number 2. It is going to pass near the black hole. The concentric lines indicate the power of the black hole's distortion on space-time, weakest on the edge, and that it's most powerful in the centre. Spaceship 1's clock starts to slow down as it passes into the sphere of influence of the black hole. Time begins to slow down. When it enters the inner region, it is travelling near the speed of light, and so for Spaceship 1, time stops completely. If Spaceship 1 now rendezvous at Spaceship 2, we see that Spaceship 2 has aged much more than Spaceship 1.
been able to do experiments with subatomic particles that actually prove this happens. There's a classic one of these particles called muons that hit the Earth's upper atmosphere, or created when particles hit the Earth's upper atmosphere, and they're unstable. Half of them will vanish in a very short period of time, thousandths of a second. And so you know how many are being produced if you measure them at the top of a mountain. And if you look at the bottom of the mountain, which as they come down very fast, close to the speed of light, you can figure out how long that would have taken, a few thousandths of a second. And you know that a certain number of them should have decayed, vanished, because they're unstable. And when you measure that, it turns out that there's a lot more than there should be. So their clocks have to have slowed up. And it's a very easy effect to measure. And that sort of proved that this idea of time dilation was correct.
I see.
And justified Einstein's theories of relativity.
They sent clocks on an airplane back, I think it was back in the
Yeah, that was an early experiment done as well. They flew two aircraft away from each other at very high speed with very accurate clocks on board, and then compared them when they came back. And there was a tiny discrepancy around about what you would expect from theory of relativity. Even the GPS satellites we have, they actually have little routines built into their calculations that allow for the effects of relativity, the fact that they're going around so fast in a gravitational field of the Earth. And if that wasn't done, your GPS systems would be inaccurate. So you wouldn't be able to navigate if it weren't for the theory of relativity.
Well, they mustn't be doing it to my GPS, because it often sends me in places where I shouldn't be. Well, absolutely fascinating stuff there, David. We could talk about this all day. It's absolutely mind-blowing, but unfortunately we've ran out of time. So thank you very much for joining us today.
It's been a great pleasure, and thanks very much for having me.
And if you want to find out more, you can catch up with David at astronomy.ie to find the Astronomy Ireland website. And you can catch up with us, of course, on neartv.ie. I hope you enjoyed the show. Take care.